Bismillahirrahmanirrahim. This video is about transistors, and here we'll be primarily solving example 6.9 from Mr. Sedra's book. Let's go through some of the concepts. We had already learned these three modes of operation: the saturation mode, the active mode, and the reverse mode. Now in reverse mode, the base emitter junction is reverse bias, and we are not concerned in this lecture with this, so we'll do away with that. So we are only left with this. Now if you note, both of these have base emitter forward biased. So when base emitter is forward biased, there could be two situations, as we can see from here. The circuit could be either in active mode or in saturation mode. Now how to determine this? One way is that we find the collector base voltage, CV junction voltage. So this voltage will determine whether the transistor is in active mode or it is in saturation mode. If this is reverse bias in active mode, this is forward bias, it will be a saturation mode. So we are concerned with these two, and if you look at this diagram carefully, this is between VCB and current IC, and from the diagram we can conclude that although this diagram gives a general idea about the mode of operation, the practical active mode starts from VCB -4. Look at here. VCB up to -4 is the active region, and then beyond -4 it is saturation region. What does this mean? That VCB greater than -4, that is -3 or -0.3, -0.2, on this side is the active mode. And for VCB less than -4, this is saturation mode. Now keep in mind that in the active mode we have the maximum current, but as we move towards the saturation mode, the current is decreasing. So this we have to keep in mind. Okay, so VCB from here is -4. Now here I have written two symbols, VCB and VBC. Both are written in the book. When the positive sign is towards the collector, then it will be called VCB. When the positive sign is towards the base, it will be called VBC. And the difference between the two is nothing but the change in sign. So when we are saying VCB -0.4, we can also write as VBC plus 0.4. And this point is actually the border of active and saturation mode. There is another way of saying that as long as the collector voltage, this collector voltage, does not fall below that of the base by more than 0.4, the transistor will be in active mode. So let's see from here. If VB is 0 and VC 0.5, no problem, 0.2, no problem, even 0, no problem, the transistor is in active mode. But even if it is -4, -0.4, still the transistor will be in active mode. When it becomes -0.5, then it will go into the saturation mode. Okay, comparison between NPN and PNP. Now here ultimately we'll come to the VCE. Now from this diagram you can see VBE, we know, is the base emitter is always 0.7 generally. VBC or VCB, from here we are saying this is -0.4 or plus 0.4, also VBC less than 0.4. Therefore, VCE will be greater than 0.4 or equal to, and this we can find from this relation, the loop equation around this. Minus VB plus VVC or minus VCB. Minus VCB plus VCE is equal to 0. Putting the value of 0.7, 0.4, we find VCE to be, it has to be 0.3 or greater than 0.3. So this is one condition for the active mode. And when we move here on the left hand side, that means at 0.5, then we are actually in the saturation mode. So when VVC is approximately 0.5, then we are in saturation mode, and in saturation mode VCE will be 0.2 from this formula. So these 2 points are important to distinguish whether we are in saturation mode or we are in active mode. Similarly for NPN, not much change except that the nomenclature or the names have changed. So here it is called VEB, here it is called VCB, here it is called VEC. The basic concepts remain same. For active mode, it is 0.3 or greater than 0.3, and for saturation, it's approximately 0.2 volt. Now, there is maximum collector current term has been used in this question. The maximum collector current is actually the saturation current, I said. And the easiest way to find this is that we put VCE in whatever circuit, we put VCE is equal to 0. So in this case, if you put VCE is equal to 0, from here we can calculate IC to be VCC over RC. So this is the easiest way of doing. But if the circuit is slightly more complicated, like we have RC and RE, still we can use the same technique, put this is equal to 0, and then IC saturation in this case will be VCC divided by the two resistors. And finally, we'll discuss the condition for a transistor to be in saturation, which we'll use to prove whether the transistor is in saturation or not. So the first condition is that the saturation current or the saturation collector current, IC sat, should be less than IC of the active circuit. The other is that we can calculate B forced, which will be IC over beta, and this B forced should be less than the given value of beta. Now let's come to the example 6.9. We want to analyze the circuit to determine voltages at all the nodes and the current through all the branches, and beta is given to be 30. Minimum value of beta is 30. So generally the technique followed is that we first assume that the transistor is in active mode, calculate all the voltage, currents, etc., and if they are consistent, then we accept that. If they are not consistent, then we assume the transistor to be in saturation mode, and we again determine the parameters. Let's see how we solve this question. First of all, I have marked the voltages VE, VC, and VB here, and then we'll keep this circuit in mind. PNP, forward biased, and the others we don't know whether they are forward or not. So depending on these, we can say whether the transistor is in saturation or active mode. Now in this case, if you see, this is just opposite. Here is the emitter terminal. So base emitter is forward bias in this case also. And so now we have to find whether they are in saturation mode or in active mode. Since base emitter junction is forward biased, the transistor will be either in active mode or in saturation mode. So as we mentioned in the previous slide, we have to assume it to be in active mode first of all. So assuming in the active mode, and then we are neglecting the base current in this 0. Therefore, the VB will also be equal to ground or 0. So VB will be 0. And if VB is 0, then VE, this one will be VB plus VBE. So VB plus VEB. VB we had assumed to be 0. VEB we know is 0.7, the base emitter value. So VE will be 0.7 volts. So this will be 0.7 volt. Okay, so now that we have this VE, we can calculate the current IE. For that, we have just drawn the various currents IE here, IC, IB, and IE now you can see is 5 minus 0.7 divided by 1K. So this is IE 4.3 milliampere. So IE found, now we have to find the current IC. So we'll calculate IC in two ways. First of all, calculate IC in the active mode, and this will calculate from the formula, because these formulas that we had learned earlier, they are valid only in active mode. So using this formula, we can find IC. So IC is alpha, IE alpha we can calculate from this formula, putting in the value of beta, here IE. So IC in active mode is 4.16 milliampere. Now we'll find IC saturation or IC maximum that we discussed. And as I mentioned, that the simplest way is that we use VCC over RC. So 5 over 10K or minus 5 here, you can see VCC minus 5 over 10. So the current is 0.5 milliampere. And now we are in a position to compare between IC saturation and IC active. And for the condition of saturation, IC saturation has to be less than IC active. And this we can also see from here. This is IC active, and IC saturation is going down, that is reduced value. So IC saturation has to be less than IC active if we are operating in this region, if the transistor is saturated. And so we can see in this case that 0.5 milliampere IC saturation is less than 4.16 milliampere, and therefore we can conclude that the transistor is in saturation. Now this was the simplest way of finding, which has been done in the book, but I would prefer it to use this method, that since this is our circuit, we'll put this equal to 0, and from here we can calculate the I saturation, which will be about 0.9 milliampere. Still this condition is valid, that 0.9 milliampere is less than 4.16 milliampere. Anyway, now let's proceed. Now that we have established that the transistor is saturated, we proceed as follows. The first point we have to keep in mind that when the transistor is in saturation mode, VEC or VCE will be approximately 0.2. So we'll write 0.2 here. We'll write 0.2 and then we'll solve the circuit. So first VE as we have learned, it is VB plus VEB, VB plus VEB. Now in this case we don't know what is VB. Earlier we had assumed it to be 0, but now it is not. So VB is unknown. VEB we know is 0.7 always. So this is one of the equations. Similarly, we'll find VC. VC from here, you can see VC is VE minus V saturation. So VE minus V saturation is VC. VE will put from here. V saturation is 0.2. So this is our equation for VC. Similarly, IE. Now IE, look here, is 5 minus VE divided by 1K. So 5 minus VE 1K. Putting in the value, simplifying, so we get this term. And finally IB. IB will be VB divided by this resistance 10K. So VB divided by 10K is 0.1 VB. Now all and finally IC. IC is also we can find from here VC minus 5, and putting in the value of VC from here, solving, we get this term. Now all these terms are in terms of VB. Since we don't know VB, we have to first of all find VB. So we were here, we had all these values in terms of VB, and now we'll try to find VB. We know the relationship that IE is equal to IBIC. From here, IE is equal to IB plus IC. Putting in the values of all from this and solving, we can find VB to be 3.13. Now putting VB 3.13 in these, we calculate VE, VB, VC. So this is the final value of all the parameters. Now we'll again try to verify this using the beta, and we have learned earlier that beta forced, which is equal to IC over IB, should be less than beta given for the transistor to be in the saturation mode. Now why it is called beta force? My guess is that since we are operating in the saturation mode, this formula is actually not valid in the saturation mode. It is valid in active mode, but since we are trying to calculate or forcing to calculate, therefore the name beta force, forcing to calculate in the saturation mode. So beta force will be IC over IB. From here, putting in the values, beta force will be 2.8 and beta given is 30. So this proves that is 0.28 is less than 30, or beta force is less than beta given, and therefore it is, again we can say that the transistor is indeed in the saturation mode or saturated. So I hope this gives you an idea how you can solve this question by following these steps. Thank you.